GTT in our space-time theory comes about from gravity. We're certainly going to expect it has a lot to do with gravity. So now we look at the chart that we had. We had three levels. We had, in gravity, the tidal acceleration. Underneath it, it came from what? What led to the tidal acceleration? The gravitational acceleration. Right? The difference between the gravity. The parallel to this in space-time geometry was what? What's the parallel to the tidal acceleration in space-time geometry? Okay, we had tidal acceleration, which were these things. Okay? What led to them? It was these A primes and so on. It was gravitational tidal acceleration, gravitational acceleration. You can build up the tidal acceleration from these guys.
Right.
What's the corresponding space-time geometry thing? The Riemann.
Right.
Riemann curvature, right? Because that's the tidal, that's the relative thing of neighboring geodesics. What's the corresponding space-time quantity here?
The world line.
World line curvature, connection curvature. The connection. Now we're supposing that there's a third level here. Okay? There's a GTT and so on. Okay, there's G, there's a space-time metric. What's going to be the thing that builds up here? So the one thing that we know of is the potential that leads up to this. The question is there really any relationship between these two? But this is the immediate candidate, phi. Okay? So now what we're going to look into is what is this gravitational potential? And how is the gravitational acceleration built up from it? What is it? Why is it? What does it look like? You know. And when we're doing this, we're keeping in mind that we're talking about not just the gravitational potential, but we're talking about a candidate for a space-time metric. And in fact, we'll see that that's exactly what it is. And this thing is very much phi r. That's pretty amazing. That the space-time metric has as a function in the coefficient of dt squared simply the phi gravitational potential. So you can already see that there's going to be time effects due to gravity. All kinds of interesting things happen. In fact, what this tells you is if you measure, if I look at my watch and I measure a certain amount of time over here, right, it's affected by phi.
Right, so
if I measure it somewhere else,
accelerating or something, then it'll change.
well, I don't even have to accelerate. I can just stand over here and look at my watch.
Oh yeah, you don't even have to move.
And my phi is different.
Right.
So what's going to happen is my metric of time is going to be different. The amount of time that I measure, and you can do this.
So does this affect like global evolution satellites?
Things like this, yeah. Well, things that come from this theory affect it. I mean, I don't know exactly which effect is most, and maybe we'll be able to solve that problem. But if you just go at this floor, we're on the 4th floor, the rate of time passage here is different than the rate of time passage where we were on the 6th floor. There's an actual difference. It's obviously a minuscule, tiny effect. And it has nothing to do with special relativity. It's not speeds.
Why is it different?
Because phi is different. So phi delta t gives you the amount of time. I mean, it's something that, again, it's so counterintuitive when you would think about it. Say there's a metric to space-time, isn't that? And there's this coefficient. What is the gravitational potential? There's a non sequitur here. What does one have to do with the other? But when you build it up this way, you can see that this is very reasonable to suppose, but we're going to look at it a little bit more carefully.